Okay, so again good morning to all of you. So we will start lecture 7 today, which is going to be a little bit based on Bravais lattices, and if time permits we will start with symmetry in crystals. So let me just give you a brief recap. We discussed about primitive non-primitive lattices in the last class, and what is the motif or basis, and how is the relative orientation of atoms and molecules in the motif determine whether you will have what kind of primitive unit cell you will have. The key thing is that one must follow the definition of the primitive lattice, that is, within the primitive unit cell, that it should be a repeatable unit. It should not be, there should be no gaps or discontinuities. It should be repeatable. So if you choose a smallest possible cell which must take into account the orientation of molecules with respect to each other, should be such that so that it is repeatable and it has identical neighborhood for all of the species associated. So let me now go to the next topic. So we have seen that there are 7 crystal systems and there are 14 Bravais lattices in 3D, and what we also saw that each non-primitive lattice, such as face centered cubic or body centered cubic lattice in case of cubic system, is composed of number of primitive lattices depending upon the number of lattice points. So for example, body centered cubic has 2 lattice points, which means it is equivalent to 2 primitive cubic lattices. Similarly, face centered cubic lattice has 4 lattice points, it is equivalent to 4 primitive lattices. So one should be able to draw the primitive lattices within a non-primitive lattice easily. In a non-primitive lattice also as a result, what we will do, just give a brief flavor of that you can draw a primitive lattice by drawing the I think there is a mistake here, we should just one second. Okay. So by translating along, so let me just cut this word drawing, it should be by translating along the lattice vectors. Okay. So let us see how we do that. So this is, for example, a primitive lattice. Okay. It is in 2D. Okay. So this is a 2D primitive lattice. In this, what we have is array of atoms, and you can see that so we have drawn the first primitive unit cell, which is this unit cell, this number 1. And you can see that A1 is the primitive lattice vector, A2 is the primitive lattice vector. But you see, as we said in the beginning, the choice of primitive cell is not unique. So essentially you can choose any vector which can give rise to a primitive unit cell. So you can see in number 2 you have primitive lattice vectors as A1 prime, A2 prime however is different, it is not same as A2, A2 prime is from this atom to that atom, but it still gives you a primitive unit cell. The area of these 2 cells are going to be equal to each other. You can see in third one you have this A1 double prime and A2 double prime. Okay. So choice of primitive lattice vectors is, you can have multiple choices, so it's not a fixed choice. As long as you are able to make a primitive unit cell out of those 2 vectors or those 3 vectors in 3D, it's perfectly legitimate. Okay. Similarly, you can see that in this case, in the case where you have this A1 triple prime and A2 triple prime, you can see that this is the unit cell that you are drawing, which is a non-primitive unit cell, which is a bigger unit cell. Okay. Similarly, there are multiple choices of non-primitive unit cells as well. So in this case, this is one unit cell, you can have one non-primitive unit cell like that. This is also a non-primitive unit cell. So this could be a lattice vector, that could be a lattice vector. So basically what I am trying to emphasize upon is, when you choose a particular primitive unit cell, the choice of primitive unit cell vectors is multiple. Okay. Provided those vectors always give you a primitive unit cell of same type, of same area. So in BCC, for example, this is a case of BCC lattice. In case of BCC, so in case of BCC, there are, so I have given you 2 choices. The first set is A1 vector could be AX hat, A2 could be AY hat, and A3 can be A by 2 x hat plus y hat plus z hat, which means this is, so this is A1, this is A2 here, and this is A3. Okay. So A1, A2, A3, this is a set 1. You can have this lattice vector, this set of vectors, and still construct a primitive lattice, or you can alternatively have another set of vectors which seems more convenient in BCC. See, what you choose is dependent upon the symmetry, but there are multiple possibilities. Okay. So this is A1, A1 could be this one from here to here. So let me just change the color of this particular thing. So this is A1 here. A1 is half of A by 2 y hat plus z hat minus x hat. This is A1. This is for the, so you can see that this is a BCC unit cell, all right. So we are taking the atoms which are down there. Okay. This is the one in the center, this is on the right side, this is the atom below, and this is the atom which is somewhere on the downside. Okay. So you can see that we are going from, so this is in this case it is y plus z minus x bar, but you could have very well chosen, so if you for example go from here, you could have chosen from here to here, this could be one lattice vector. So in this case we are taking this as a origin, that is why we have chosen the atom which is down there. So there are, so you can see that this is y, this is x, and this is z. So this vector is half of y, okay, in this direction, half of z which is in this direction, and then half of x. So half of, now remember positive x is in this direction, so we have half of x negative direction, half of y, and half of z, and we will reach here. So this is facing you, right. So it is in this direction, this atom. So this is within the cell, this is outside the cell in front of you. This is to the right of the central atom in the unit cell, this is the bottom of the central atom in the unit cell. So this is A1 vector from here to here, this is A2 vector from here to here, and this is A3 vector from here to here. So you can see that one is half of y plus half of z minus x half of x, this is half of z half of x minus half of y, and this is half of x half of y minus half of z. And by correcting these vectors you can make a unit cell, something like that. This, so if you try doing this exercise using either of the, so you have lattice, you have the lattice translation. Now you just connect them with each other, and you should end up with something like that. So this is a primitive cell. And its volume is half of the non-primitive unit cell volume. This is in case of FCC. So in case of FCC you can have vectors. So this is, if you choose this as an origin, this is A1, so this is A1, this is A2, and this is A3. So basically corner atom is connecting to 3 face centers atom. So as a result, A1 is half of y plus z, A2 is half of z plus x, and A3 is half of x plus y. If you choose your origin differently, your vector signs and they will change. So if you connect from using these 3 vectors, you get this parallelogram or parallelopiped in the within the cube. This is the primitive cell. Okay.
How do we get these vectors?
Shortest lattice translation.
Okay.
That is basically it's a lattice translation. Lattice translation is you go from one point to another, then from, so for example, if I go to previous slides, so lattice translation is you choose this as the origin. Okay. Now if you go from here to here, you get a point, lattice point. You go from here to here, you get a lattice point. Similarly, in this case also, you went from here to here, you got a lattice point. You go from here to here, you get a lattice point. In this case, you go from here to here, you get a lattice point. Then again you go from here to here, you get a lattice point. So it's a lattice translation vector. So choices are unique. You go from one lattice point to another lattice point.
But in case you are telling that FCC and BCC,
Yeah.
those are non-primitive unit cells.
Non-primitive unit cells, but non-primitive unit cell is it does consist of primitive. So in this case, what is the shortest lattice translation vector? That is what we look at. So that is the primitive lattice vector. Okay, that is the primitive lattice vector. Because a non-primitive cell is made up of 2 primitive cells, right? So you can always choose a primitive lattice vector within the non-primitive set. Non-primitive lattice vector would be, you have a cube. So non-primitive lattice vector would be this, that and that. But these are shortest lattice translation vectors which are primitive lattice vectors. So I think in one of the earlier classes I asked you to draw 2D lattices which are possible. So there are few possibilities. You can see the first one is A is not equal to B and theta is not equal to 90. Other two possibilities are A is not equal to B but theta is equal to 90, and third one is A is, so in this case you can have A is, this is centered lattice, okay. So A is not equal to B, theta is equal to 90 degree, but you have an atom in the center. So this is a rectangular centered lattice. So this is a oblique lattice, this is a rectangular and centered one. This is hexagonal, in which A is equal to B, theta is equal to 120 degrees, all right. And then you have a square lattice where A is equal to B and theta is equal to 90 degrees. So these are the possibilities which exist in 2D, 5 possibilities of Bravais lattices, all right. So now we have been talking about primitive and non-primitive unit cell, and we have also said that there are multiple possibilities of primitive unit cells. One can have a square depending on the type of arrangements, you can have a parallelogram, you can have different shaped parallelogram. So multiple possibilities are there provided they have only one lattice point per unit cell. The question was, how do you define a criteria so that you do not end up with multiple possibilities? How do you fit them into certain criteria? And that is where the system of this crystal system came into being. So crystal system is the classification according to crystal system. You could see that there are certain criteria based on lattice parameters and there are correlations. So how do you get this criteria? This is, as you can see, this is based on symmetry, right. So you can see intuitively that a cube is more symmetric as compared to tetragon, right, because cube has 3 sides which are equal, it has all 90 degrees angles, and but tetragon has all the 90 degree angles, but it has one side which is different as compared to other two. The question arises is, what is this criteria ad hoc, or is there some scientific basis around it? And we will see in the coming few minutes that there are certain crystallographic symmetry considerations which have to be followed to evolve this criteria, and we will now take up those symmetry criterion in next few minutes. So what we now start with is called as let me start with symmetry in crystals. And why do we need to understand this? So that we can understand the logic behind the basis of crystal system classification and choice of Bravais lattices. Okay. This is a very complicated topic, so unfortunately in this course we do not have enough time to get around complete aspects of crystallography, but we will try to just establish a simple basis how to deal with it. Okay. So, so what is symmetry? That is the first question. So the answer of this question is, symmetry is an operation which brings an object into its original state. Okay. So for example, if I take this square, okay, so what is the symmetry operation? I can perform on it so that it remains, it looks the same. One possible option is, if I choose this as a center of square and I turn it by 90-degree rotation around this axis. So, the axis is perpendicular to the plane of the paper. So, if I apply 90-degree rotation, then this again looks the same, right? It comes back to square shape. So, this is 90-degree rotation. So, this is called as rotation symmetry. Similarly, if you take a triangle, equilateral triangle, what operation do you need to perform on it? So, this is the center of the triangle. Let me say this is the center of the triangle, and I provide a 120-degree rotation. So, it appears in the same shape. So, these are just examples of operations which you can perform to bring the object into the same shape. So, why we need to understand this, because lattices are classified by their symmetry. So, it is not only this rotation which is one symmetry element, there are multiple symmetry elements. So, what are these symmetry elements? So, as I said, symmetry is an operation which you perform on when you perform on an object, you bring into the position of self coincidence. So, let us now look at what are these symmetry operations, types of symmetry operations. So, types of symmetry operations, actually first one we should call as translational, because if you start just from 1D lattice. So, let us say if you have this case of 1D lattice, okay, and you just put an atom here. So, you can see that if you move from this point to that point by a vector t in an infinite array of points, okay, in 1D, then this lattice translation vector t brings me into the position of self coincidence, because if this point is identical to that point, then this is the translation. So, this is a case of what we call as a translational and this is a defining symmetry in 1D. Okay. In 1D you must have translational symmetry. Now let me do one more thing. If I change the motif around it, so this is again in 1D. Instead of keeping motif as one atom there, I keep motif like this. Okay. So, what I have here is I have translation T, but I also have a what is it? Mirror. So, I have translation as well as, so I have translational and mirror symmetry. Okay. You can make this little worse, you can make the mirror disappear if you make this so let us say this becomes dark. So, mirror has disappeared now, right, but it still has, because the motif now is, so motif initially was A, now it is AA, now the motif is AB. So, motif, this is the motif in this case, this is the motif in this case, this is the motif in this case, but now you have translation, but no mirror. So, in 1D you can have operations which are called as translation and mirror operation, reflection, we call it reflection. So, translational symmetry and Okay. So, these are two symmetry operations, translation, reflection, they apply to 1D, 2D, 3D, all of them, but they are but the only two cases which are possible in 1D are these two. So, let us move to little bit more complicated. So, let us now go to let us say 2D. Okay. So, we have seen two of them, translation and mirror, they are applicable starting from 1D to 3D. Okay. 2D, there is addition of what we call as rotation element, all right. So, for example, if I take this lattice Z, what is the rotation I need to provide on it to make it, to bring it into self coincidence? I need to rotate it by, so theta is 180 degree. So, if I rotate around this point by 180 degree, it will become, it will come into same shape. So, now in case of rotational symmetry, we define this as fold, n fold symmetry. So, n is number of fold of symmetry, and what is this n? N is basically 360 degree divided by theta, angle of rotation. Okay. So, this is the angle of rotation. So, in this case what will n be? It will be 2. Now, how can you make a 2D lattice out of this? Let us say I have make a 2D lattice like this. If I make this as an object or basis, so let me first complete this part. Okay. So, this is 2D object. In this case, if it is equilateral triangle, it will be theta will be equal to 120 degree, n will be equal to 3. In case of let us say this symbol, which you are all familiar of, so this is theta is equal to 90 degree, n is equal to 4. And if you look at some flower, it is not very symmetric, but so some flowers have 5 petals. Better, right? So, you have 5 petals here. So, here you need to provide a rotation of 72 degree, 5 fold. If you look at the ice flakes, or if you look at things like this, their ice flakes are something like that. They are sort of 6 fold symmetry. So, here you need to provide a rotation of 60 degree, and this n will be equal to 6, and you can also have things like 8 fold symmetry if you have 45 degree rotation in case of certain objects. So, there are no 7 fold symmetry, you can see there is no 13 fold or 11 fold, all those are absent here. So, and there are mathematical bases that why I cannot get into details of that, but 7, 11 you can see that here 9 is missing, 9 fold is not there, 13 fold is not there, all these are missing here, 7, 9, 11, 10 fold, all of them. In fact, even 5 fold is not permitted in crystallography because it does not fill the space. See, the point is you can have a rotation of that degree, but if your object does not fill the space. In crystallography, the important thing is in crystalline materials, that operation must fill the space. Okay. So, 5 fold object do not fill the space. So, as a result crystalline materials do not show 5 fold symmetry. There is another class of materials which show 5 fold symmetry are called as quasi-crystalline materials, but they are non-equilibrium materials. So, similarly other symmetries are also shown by those materials, 10 fold symmetry or 9 fold symmetry. They could be shown by some materials, but they are not seen in crystalline materials normally. So, in case of crystalline materials, what we are interested mostly in is in 2-fold, 3-fold, 4-fold and 6-fold and 1-fold symmetry, of course. So, here and the graphic symbol for these symmetries is, this is shown like this is shown like this is the symbol for 4-fold symmetry, this is the symbol for 5-fold symmetry and this is the symbol for 6-fold symmetry. Okay. So, now let us come back to this lattice which I have drawn. So, you can see that in this case, in this lattice, so if I provide a rotation around this point, then even a 2-fold rotation is possible. Is there a 3-fold possible? There is no possibility of 3-fold. 4-fold is possible, 6-fold, 5-fold are not possible. So, this has 2 and 4. So, of course, around this point it will have 4-fold, but 2-fold you can also have at these points, right. So, basically you define each of the point by maximum possible symmetry. So, this center here, this can provide you 4-fold. So, although it can also provide you 2-fold, you depict it by 4-fold, because 4-fold is the highest symmetry that you can achieve by rotating around this point. So, similarly around these points, these are depicted as 2 points because they cannot give you 4-fold, they can only give you 2-fold. So, you depict these symmetry points, rotational symmetry point in the lattice in this manner. Now, you can see that if you have, you can have a square lattice, and if I choose a motif which is symmetric enough or which is circular, you get 2-fold and 4-fold. But now let us say the lattice is a square, but I replace the motif by these triangles. So, I have changed the motif now. Does it have 4-fold or 2-fold symmetry? It does not have 2-fold, no, it has no 4-fold. So, what I mean to emphasize here is we cannot go by the conventional definition of what looks symmetric. We have to go by these definitions of symmetry which make it very specific. So, although it looks like a square grid, it is actually not a square lattice because it does not follow 4-fold, it does not have a 4-fold symmetry, it does not even have 3-fold symmetry, because if you perform 3-fold symmetry operation, it does not remain the same. The only operation you can perform on this is it has only 1-fold symmetry. You can see that it has only 1-fold symmetry, rotational symmetry. So, this is why in crystallography a cube may not be a cube if it does not have elements of symmetry that are specific to cube, which I will come to in a short while. Okay. So, let's wind up here and we can now take to the next lecture.